In this video, we are talking about week 5 of ENGG 201, where we're talking about the behaviors of real gases. In our previous video, we talked about the behaviors of ideal gases, and adding on to our knowledge of ideal gases, working with real gases will allow us to make better estimates about different values of gas. So the first equation that you're going to see here was developed by a scientist whose first name I do not know, but his last name was van der Waals, and he created an equation used to describe real gases, where our P is our pressure of our gas, our Vm is our molar volume, we have our R as our gas constant, our temperature in Kelvin, and we have two new components to add, new variables. We've got A, which is one of our coefficients, and we've also got B, which is another one of our coefficients. And through unit analysis, we can see that this is equal to, so let's practice some unit analysis. So we know that molar volume, so these two must be equal in units in order to subtract them. So that means that this is worth meters cubed per moles or kilomoles or what have you. So just volume over moles. It's the most general way to describe it. And now let's look at this one here. So molar volume squared, this is, okay, so we've got our pressure. So this is our mass per our area. And this has to be equal to, so we've got some unknown A, and 1 over our volume over our moles. If we flip that around, that becomes moles on top, this in our bottom. So in order to balance this out, that means we have to have moles in our bottom for A to cancel out with this term. We need to add a mass term to the top, and we need to cancel out our, hold on. This is to the power of 5. And we know that our M times 2 of our L's, so we can split that up, is pressure. So that gives us, and that leaves 2 left. So that's pressure, so volume over moles. Right, sorry, let me just illustrate that a little better. So we take that 5, and we're going to break it up into 2 and 3. This becomes equal to pressure, which we saw from our left side. So that's how we got our values for A and B. Okay, so this is our most standard form of our van der Waals equation. But once we rearrange to isolate for pressure, it could look like that. And in terms of our molar volume, it would look like this. Now there's another step to simplify this even more. So let's move these terms over to our right side. Let's move all of this over. So then we just equal to, so that's molar volume to the power of 3 equals, then we're going to move all of our stuff over. So this is B plus RT over P, molar volume squared, plus A over P molar volume minus AB over P, and this is equal to 0. Now let's make this just equal to molar volume on this side. So we're going to divide everything by Vm squared. Right? And that is going to give us Vm equals, so these terms are going to cancel out. So this is just B plus RT over P. That's our one term. Plus, this is going to cancel. That's going to reduce. So this is, you can write this as AP times, right? So that's just A over P M. And this is minus AB. Oh, sorry, this is meant to be plus. Sorry, plus and Vm squared. Okay, and you're going to see that this equation is going to be used a lot when we are using our equation of state to calculate values of molar volume for our for our equation of state. So for the van der Waals method, there's a couple things you need to know. You need to know how to get A, and you need to know how to get B. So once you find those, so hold on, let me add these up. Let me just start writing it out. So find A and B if not given, and make sure you're watching your units to make sure it's consistent with the question you're given. Second, find average A and B if needed. So if you're working with a system that has, so I'm going to say mixed system. So if you're working with a problem that has more than one type of gas, you're going to need to calculate A and B for each individual gas, and then use these addition rules to add them together. So for B, simply just take the mole percent, the mole percent, and then multiply it with the B that you got for that specific gas, and you can add them all up. And for A, you would take the square root of the A value you got, multiplied by the mole fraction, and take the whole sum of all of them squared. Right, so there's specific adding rules that you need to adhere to. So the third step is use ideal gas law to find a starting molar volume. Okay, so I'm going to try and explain it here. It'll make a lot more sense when we work with examples. The molar volumes that are distributed on the right side of our equation are going to be different. So these are going to be, so I'm going to mark them just with a 1. Those values are going to be different than the one that we're solving for. So we're solving for this one on the left side, right? And we want to plug our estimates in each iteration into here. So these are estimates. So to start, we're going to just use our PVM equals RT equation to find our VM. To start off, using the ideal gas law, and then we're just going to keep using this equation of state over and over again until we get an answer that's close enough. So usually it'll ask you how many iterations it wants you to perform. Good rule of thumb, do more than one. So do at least two iterations. And then you'll find your molar volume. Okay, so it'll make more sense once we do an example. Here are some other equations that we will be using. We have critical pressure, critical temperature, which is solved using A and B. And we have critical volume as well. Okay, so next we're going to talk about the Z-chart method to solve for compressibility factor. where Z is equal to our pressure and, so just use this equation here. And if we were to rewrite this, this would look a little something like this. On the on the right side of the equation, that Z is going to be acting as if it's a coefficient to this RT. So there's different ways to solve for our Z. This first method requires graphical analysis. But we have to calculate for some in-between properties. So if I were to run through, I would calculate critical temperature and critical pressure, if you haven't done so already. And then you're usually given your initial state values for temperature and for pressure. And you're going to use that to calculate reduced temperature and pressure. And these are the axes of the graph that we're going to use. So say, for example, you had a, what is this? Okay, so these lines here, so these curves, these are reduced temperature. And they're isotherms. Ooh, my spelling is crazy. Okay. So say we had a reduced temperature value of 1.20. So let's start with this line. Let's follow that curve all the way till over there. And let's say we had a reduced pressure of 3.0. To find our compressibility factor, we're going to read from our x-axis line up vertically until we hit our reduced temperature curve. And then when we read across, this will give us our compressibility factor. So we can say that's about like 0.57, for example, right? So then that's what we're going to be using for our coefficient, for our compressibility factor. So we're going to read TR and PR to find Z, and then put Z back into equation. Okay, awesome. So here's another method for finding Z, and we are introducing a new variable called eccentricity. This is what it is equal to. Usually eccentricity is given to you in your question. I haven't encountered a question that doesn't, but if you want to know how to find it, you can use this equation here. That's where it comes from. Okay, so the Pitzer-Curl method involves finding the reduced temperature and pressures of your gases. So I would find reduced properties, and then read off graphs. So you have to do 1 for Z to the power 0 and Z1. So there's two different kinds of Z terms you have to pay attention to in this equation. You have ZO, and you have Z to the power of 1. And this is our full equation here. So it's a function of these two variables. So basically, just to put it in more plain terms, this is equal to plus eccentricity, which is represented by omega, and this is z to the power of 1, and this is equal to our plane z, which we use in the same way with our other equations as such. Okay? So once you read off your graphs, then just plug and be on your merry way. I'm going to say interpolate if needed. I'm going to talk about interpolation. Okay, so this is what your Pitzer-Curl tables look like. So say your reduced properties are 1 for your temperature and 1.4 for your pressure. You're going to read along this axis and see where it intersects with this one. So that would be 0.250, and this would be equal to Z0. Now to find Z1, same process. Let's find, here's where they intersect. So then this gives negative 0.099. Okay, so what if your values are in between? So what if your values fall somewhere in between two different points? Okay, so we're going to talk about that. So the relationship between these properties is expected to be linear. So because of that, the distance between, so if you had 3 points laying on a line, right, and your unknown point of interest is in between, linear interpretation just basically says, interpolation just says that the slope between these ones is equal to the slope between our two endpoints, right? Because it's a linear line, slope is consistent. So basically, if we are solving for an unknown, then we could use this property here to estimate, right? So if I want to find what's in between, like 1.36 and 4, let's make this more like 1.5, right? And I have a value in between here that I want to know, and a value in between here that I want to know, and I had 0.5 and 0.6. Let me just make this look like a chart. This is x and y. Slope is y over x, right? So you want to make the slope of these 2 points equal to the slope of any other 2 points that include the unknown, right? So if we write that out, this could be, so 0.5 minus 0.6 over, in our x values, let's make sure they match up, minus 1.5. And this is equal to saying 0.5 minus our unknowns. So say we're given that one, so I'm just going to write a squiggle. And then that way we can solve for our x, whichever we're looking for, whatever that may be. Okay, next is pseudocritical temperature of and pressure of mixtures of pure gases. So this is just another way to visualize some of the adding rules for questions like these. Right, so you need to be able to know how to do that. Okay, so that brings us to the end of our notes section. Since we haven't spent much time here, let's move straight to our practice questions. Okay, so this is a midterm example from a while back. Okay, so there is a gas mixture called hydrothermal gas, and it's composed of 3 different components, which are specified here, stored in 100 cubic meter vessels at a specific temperature and specific pressure. So we need to determine some properties below. So pseudocritical, we just talked about that, so let's just move on with that really quickly. So pseudocritical temperature, TPC, is equal to our sum of Y and TCI. So we're given all that. This should be an easy calculation because we have all of our TC values here and we have all of our mole percents. So let's start with Imperium, 0.2, and that's 425.2. And it's already in Kelvin, so we don't have to worry about any conversions. This is 0.3 for second one, and plus 0.5 at a temperature of 568.8 Kelvin. And that makes our pseudocritical temperature equal to 0.2 times 425.2 plus 0.3 times 507.5 plus 0.5 times 568.8. And think to yourself now, which one is in highest concentration? That would be our last one, hypnosium, right? So we can expect our temperature to be closest to that given by hypnosium, right? And that is 521.69 Kelvin is our final answer for our first question. Next, we want our pseudocritical pressure. So going back, see it's the same story. So let's do that. So we have our moles fractions and our critical. So this is 0.2, and we're also given our critical pressures for each gas in kilopascals, so we don't have to change it. I like this example. It's a nice, easy one to start off with. Okay, and when we calculate that, 0.2 times 3,800 plus 0.3 times 0.299 plus 0.5 times 0.398. And this gives us 760.289 kilopascals. It's our pseudocritical pressure. Okay, using the generalized compressibility chart, so we're using our Z-chart method, which was our second method we covered, determine the amount in kilomoles of gas that is stored in a single vessel under the conditions provided. So let's start with the equation we'll be using. Actually, I'm gonna decompose molar volume to have N on the other side. And this is ZRT. So we're looking for our Z, right? And we're looking to find our kilomoles at the end of the day. So we're going to want to find our N, so that makes it ZRT over PV. And we're given our volume of our conditions. So if we scroll up, our first step is to calculate our critical temperature and critical pressure. And that we've already done, right? Because this is for a mixture, right? Because we have a mixture, we can't just use just our values. So we had to take the average of our values. So we already solved for those, so let's throw those in there. So we have TC is equal to this is 1, and it's equal to 760.289 kilopascals. So to calculate for our reduced properties, do I have that on here? Yes, we do. Reduced properties are equal to, so you have your reduced equals your given over your critical. So in our problem that was specified for us, so this is T over T PC, and this is equal to, so we start at 688.6. We're going over 521.69. Okay, this is 688.6 divided by 521.69. And this gives us 1.319. Right, so that's kind of in between. And for our reduced pressure, given our initial pressure over our pseudocritical, which is equal to, so in the beginning of our question, we had 5,233 kilopascals over our solved value. And this gives us 6.882. Yeah, okay. So we're going to take a look at our compressibility chart. Okay, and we're going to do some interpolation for this. Sorry, I realize I've made an error in one of my calculations over here. I was reading for eccentricity, not our pressure. I apologize. I got the first one right, though. Sorry about that. Okay, this is going to change a whole lot. Okay, there we go. That is going to be more correct. Okay, there we go. So this gives us a value of not that, and this instead, 2,908 kilopascals. Let's change this, because that's wrong. Okay, and we'll put that there instead. So 5233 divided by our answer, and this instead turns into, we're going to do some rounding. This is 1.8. I'm going to round this to 1.32. Okay, now we can take these values and we can find them on our compressibility chart. So we have 1.8 for pressure, which is about, okay, like 1.5 is about, oh no, that's 10. My bad. Okay. This is 1.0. I'd say it's roughly about here for our pressure. And we need 1.32 isotherm. So 1.32, we could say it's kind of about here, right in between. Just going to follow up. Right, and if we read up from our point, and then read across, okay, and I am reading, let's round that to like 0.95. So our Z, 0.95. And now let's plug that into our equation that we used in green above. So then this is n equals 0.95, no units. This is cubed kilomole times Kelvin. Our Kelvin of our system was 688.6 K over our pressure and volume. This pressure was given by 5233 kilopascals and 100 meters cubed. And this gives us, so 0.95 times 8.314 times 688.6 divided by 100 times 5233. And this gives us 0.01039 kilomoles. Check for units in kilomoles, right? So we can stop here. No more conversions. Okay, and now we're going to use our Pitzer-Curl tables to determine molar volume. Sorry, here's where we're going to be using interpolation. So, looking at our tables in our notes, we're going to have values that are in between. So 1.8 for our pressure, right? 1.8 for our pressure is right on the money. So we don't really have to worry about that. That gives us our nice number here. However, we are in between these 2 points because we have 1.32, right? So we're going to have to interpolate. So let's just write down our values. So I'm going to do the work over here, then I'll transfer it over. So okay, so let's start for our Z0. So we already have our reduced pressure solidified. So everything in this axis is going to be, in this column is going to be our value of Z. And then we've got our TR, so we're in between 1.3. We want to look for 1.32. So this is our unknown value of Z here, and that is in between 1.4. So if you read 1.4 to 1.8, this gives us a Z value of 0.795. And for 1.3, if we do the same thing, 0.718. So what we're going to do 0.718 minus 0.795 over 1.3. So we're using our first and last points right now. Hope you're tracking. Minus 1.4. And this is going to be equal to saying 1.32. No, sorry, I lied. This is equal to saying minus 0.795. So keep our second column on the top. And this is 1.32 minus 1.4. Let's calculate our left side because we have that given to us. So this is equal to 0.718 minus 0.795 divided by 1.3 minus 1.4. Hold on, 0.718 minus 0.795. Divided by 3.1 minus 1.4. Okay, so this gives us 0.77 on the left side. Over 1.32 minus 1.4, negative 0.8. 0.08, sorry. And we multiply that over. This gives negative 0.0616. And then when we move this 795 over, so that's plus. So our Z is equal to 0.7334. So I'm going to write our Z was equal to 0.7334. So now for our Z1, we're going to do the same thing. So we're going to find where our values are in between. Both are 0.18, so I'm going to do this in red. So for Z1, this is TR. We are again in between 0.3 and 1.4. So 1.3 and 1.4. And at our reduced temperature 8, we're going to set 1 this time. And both are 0.18. So we're going to do the same thing. Let's do... Okay, so let's do this point minus this point. So this is 0.18. Sorry, even without interpolation, we can kind of sense a pattern. So from all of these points, you see that our Z1 is consistent. So instead of calculating, we can actually just make an assumption that the Z we are looking for is also 0.18. Okay, so now let's determine the molar volume. So using the equation, PVM equals... Actually, no, we need to find Z first. Sorry, before we do that, so let's find our Z, which is equal to... But we don't have our eccentricity yet, right? So because we have a mixture, we're going to need to average out our eccentricities. And the equation for that, given that, maybe we're given that. Let me check my answer key, hold on. So in order to find our average eccentricity, so AV is the same process that we've used before, where our total is equal to times our mole percent. Okay, so we're given the eccentricity of each substance and the mole percent of each substance, so let's just use that and keep going with it. So let's see if I can fit all of that in here. I cannot. Okay, so we're just going to go back and forth. So we have 0.199 plus, I think the next one is 0.3, going up 0.299, and this is plus 0.398. And this has no units as well, so this is 0.2 times 0.199 plus 0.3 times 0.299 plus 0.5 times 0.398. And this gives us 0.3285. So that's what we're going to use to find our Z. So now we can find Z. This is step 2. This is equal to 0.7334, which we found from our table, plus the average that we just calculated, times 0.18. And this gives us, so 0.7334 plus 0.3285 0.88 times 0.18. And this gives us a Z equal to 0.7925. So now we can calculate our molar volume. So we want to find molar volume, so we're going to use, and molar volume is equal to over P. So we plug this in. Our value for Z was 0.7925. Let's use 8.314. And our temperature was 688.6 Kelvin over our pressure, which is given by 5,233, I believe. And this gives us a molar volume of 0.867, and this is kilomoles that we are using. Sorry, meters cubed per kilomole. Right, because we're using kilopascals, that means we're also using kilomoles for our units. Moving on, we're now given different conditions for the same kind of values that we started with. So to induce hypnosis, the partial pressure of the hypnosium gas has to reach 0.5 kilopascals. So that means if you separated all of just the hypnosium gas from the mixture, it would produce that pressure. So in a 100 meter cube room at 25 degrees Celsius and 100 kilopascals, we are first asked to find the amount of air initially in the room. So we can just use ideal gas law. So this is PV equals nRT. We're going to isolate for n, so n is equal to PVRT. So we're given 100 kilopascals, and our volume is 100 meters cubed. Times meters cubed over kilomoles times Kelvin. And our Kelvin is 25 degrees Celsius. And to turn it into Kelvin, we have to add 273.15. So this gives us, so divided by 8.314 times 25 plus 273.15. And this gives us 4.03417 kilomoles. Let's just trim a couple of these values down a bit. And in part 2, we want to find the minimum amount of hurlothrombic gas that must be released to induce hypnosis. So we're given the amount of hypnosium that we need, right? And we need that to be 0.5 kPa as a partial pressure. So partial pressure, I'm going to say hip, is equal to the moles of hypnosium over R times RT over V. But we don't know our, so we know this must be 0.5 kilopascals, but we don't know what this is. So our first step is find moles of hypnosium. So we know out of our total, this equals our value that we're given here, which is 0.5. Right? And we know our total moles. So this is equal to, so if we just want to find our hypnosium moles, this would be 0.5 times our total moles, which is 4.034 times 0.5. And this is 2.017 kilomoles of our whole gas is just made up of hypnosium. So now, now we want to find how to get to there. And by multiplying this by 2, we can get the minimum we need. So we need minimum of, so this just takes us back to our total. And we can say this because we already knew that our partial pressure was equal to our moles, our mole fraction. Right, so we were already there. So that is our final answer in kilomoles. Okay, so that is our first example done. We learned how to use Pitzer-Curl as well as the Z chart to find different values. And now we're going to take a look at this next question here. So we want to estimate the molar volume of the gas at sales point using ideal gas law. So what is our question? We have a natural gas that is produced in a gas field outside Grand Prairie, and it's delivered through a pipeline to a sales point. At the sales point, the pressure of the pipeline is 5 megapascals. Temperature is 20 degrees. And we have our different compositions. So I'm just going to write this in the side, because it's a good place to keep track of them. So methane, we have 0.85, 0.1 ethane, and we have 0.05 for propane. Okay, so using this information, answer the questions below. So it wants us to use ideal gas law, which is equal to NT. Oh, sorry, we don't have N because we have that. And we've isolated for molar volume. This is RT over P. And we have all those values, so let's do 8.314, and let's use times meters cubed. Are we given that? Okay, hold on. I apologize, I am going insane. Times Kelvin. And we need our 20 degrees Celsius in Kelvin, so we're going to add 273.5. And this is over 5 times 10 to the 3 kilopascals. Right, because if you had your kilopascals, which is 1,000, and then multiply it by 1,000, that gets you to 6 zeros, which is our megapascals. So then this makes our molar volume equal to this is equal to 0.487 per kilomole. Okay, and now we want to find our van der Waals parameters for A and B for methane. Okay, so we are given our formulas for finding A and B coefficients. We're given them right here. So let's use those to our advantage. Oh, sorry, we're done with this question now. We're over here. So let's find A. So A is equal to RTC and 8PC. No, sorry, 27R squared TC squared over 64 PC to the power of 1. And we have B equal to RTC over 8PC. Okay, so what do and what don't we have? So we can find our critical pressure and temperature. So we're going to find our average TC and PC. And why do we need to do that? Well, that's because we are working with a mixture of gases that all have their own different compositions. We're given our compositions and we're given the temperature and pressure of each one, critical states. So you know what to do. Find our pseudocritical, which is our sum. So this is 0.85 for methane, and that's 190.6 Kelvin. That is plus or 0.1 for ethane times 305.3 and plus 0.05 for propane, and that's 369.5. And this makes our pseudocritical, sorry, let me just separate this half. So this makes it equal to, so we got 0.85 times 190.6 plus 0.1 times 305.3, and then plus 0.05 times 369.5, and this is equal to 211.015 Kelvin. Okay, and now let's find our pseudocritical pressure. Same thing, you guys get it. So that's 0.85 for methane. What's our value? That is 46 bars. I think I want to change that into kilopascals. So 1 bar is equal to 100 kilopascals. So we're just going to take these and multiply it by 100. So that gives us 4,600. That's plus 0.1. 4,900 plus 0.05. And that's 4,250. So our pseudocritical pressure is then equal to and this is 4,612.5 kilopascals. Okay, so we're going to use these two values, and we're going to find A and B now. So A is equal to 27 times 8.314. Sorry, this is kilomoles. Kelvin. Squared, oh, this is squared too, over 64, and this is 4612.5. So let's calculate this out. This is 27 times 8.314 squared times 211.015 also squared, and that's divided by 64 times 4,612.5, and this is equal to 281.51, and this is pascals times meters cubed over kilomole squared. Okay, now for B, it's a little easier to digest. So B is equal to 0.314. This is 211.015, and this is divided by 8 times 4612.5. 8.314 times 211.015, and it's divided by 8 times 4612.5, and this is 0.0475, and this is in meters cubed per kilomole. Right, and that is our solution to this part of our question. Sorry, I want us to just quickly pretend that this is not just for methane. Oh my gosh. Okay, I did that whole calculation sequence without realizing that we didn't need to find the average. We just needed to use the parameters just for methane. I apologize. But your process should remain the same. I also realized this in pascals, so you have to multiply this by 1,000 or change this to pascals first. Okay. You know what? Okay, so that's actually what they wanted for this question. So let's just make a couple quick fixes. I'm going to do that right now. Sorry, we want this in pascals, not kilopascals. So let's change this to pascals. This is 46125. And that's what we're going to put into here. Okay, you know what? Let's restart. Let's start clean. Actually, instead, I'm just going to there's a couple things that I missed here, so thank you for your patience. I promise this is a good unit. I really liked ideal gases and real gases. Okay, so let's start clean. So right now we are only working with our methane. So methane, only doing methane. Critical temperature, 190.6. Critical pressure is 46 bars, which equals pascals. Let's keep it in pascals so we can use this unit here for pascals. So times 46, that's 10,000 times 46. And this is 460,000. Pascals. Okay, working with what we got. Let's do A first. It's 27. Then R, let's use 8.314. And that's meters cubed times pascals times moles. Per kilomoles K. right, and our Kelvin was, our critical temperature is 190.6 squared. This is also squared over 64 times our 460,000 pascals. And this is equal to 27 times 8.314 squared times 190.6 squared divided by, and this is 64 times 460,000. Okay, and there we go. This is equal to 2.302 pascals meters cubed per kilomoles squared. Okay, part B. We got our TC to PC, which is equal to 8.314. And this is 190.6 over 8 times 1. I'm going to turn this just into, whoa, my bad. Sorry, I forgot I used pen for this part. Okay, let's just pretend. Okay, got to take this out. Not really sure how to lock that layer there. Okay. B is equal to 8.314 kilopascals meters cubed. Kelvin, that's 190.6 Kelvin. And let's use kilopascals. So this is 46. And this is equal to equal to 0.04360. Okay. All right, so that brings us to the end of part B. Sorry that was such a gong show. I promise this one will be better. Okay, so this is basically just the same thing. We're given our values for A and B for our other two substances. So I'm just going to do just a brief overview since we spent so much time on the other one. In this one, you will just have to use your adding rules. So that was specified here. So you're going to take your mole fraction times the square root of each individual A that you solve for each component squared. And for B, take the mole fractions times each individual B. Right, so those are just adding questions. Okay, so let's move on to our next question. After some analysis, it has been proposed that the following state of equation can be used to describe this process here. And use this equation to estimate the molar volume of the natural gas at the sales point. So this is our equation of state method. We talked about this in this slide here. So we need to find A and B. So we've already got those under our belt. Those have already been calculated for us. So it's saving us a significant amount of work deriving that specific equation. And this wants us to use 2 iterations. So we need to find an ideal gas estimate for our molar volume to start. So let's move everything else to the other side. This is Vm cubed equals positive 0.5346 Vm squared minus 0.0560, then plus 0.00265. That's if we move everything here to our right side. And now we want to just have 1 molar volume on this side, so we divide by Vm squared. And we do that for all of our terms. Right, and this ends up giving us equals, not bad, 5346. These 2 terms cancel. This is minus 0.0560. This one cancels, this one reduces. And plus 0.00265 over molar volume squared. So I'm going to mark these with a prime to show that these are the ones that come from our estimates, right? And we use this as our new value. So we're going to start with our ideal gas estimate. Okay, so let's start with that. So RT over P, and this is given by 8.314 kilopascals times meters cubed. What? No, yeah. Kilomoles times Kelvin. Our Kelvin of our system, so we're going to go back to the very top at our sales point, which is 20 degrees Celsius, so that's 20 plus 273.15 to turn it into Kelvin. And our pressure in kilopascals was 5.6, I believe, or just 5. Yeah, it's 5 megapascals. So that makes it 5 times 10 to the 3 kilopascals. So then that is equal to, because we want it in meters cubed per kilomole, so this is, the units are consistent. And this is divided by 5 times 10 to the 3. And this we already solved for, so 0.48744. And this is our first estimate, so this is what's going to be going into the right side of our estimate. So let's do our first iteration. So we're solving for our left side. Ooh, I've run out of page. Okay. This is equal to minus 0.0560 over the value we just solved squared. Colors that. This is 0.48744 squared. And this is plus 0.00265, 0.48744 squared. Sorry, this one is squared, this one is not squared. Okay, and this gives our left side equal to, so this is 0.5346 minus 0.056 divided by 0.48744 plus 0.00265. 265 divided by 0.48744 squared. And this is equal to 0.4308. So you can see these two values are relatively similar to each other, right? As we do more iterations, it becomes more exact to our real numbers. Kind of wish I had more space for this one. So now it's our job to take this. So if we want our next iteration, we're going to take our value highlighted in green, and we're going to now plug this in and find a new value for our left side of the equation. So I'm going to see if I can translate this over to our other side. Let me just fill in some things. Okay, so now I've just put this on a different page where I've got some more scribble room. So now this is our third iteration. So what we're going to do, we want to find our next iteration. And we're going to put our new value, which we solved from our second step. So this is 0.4308 and 0.4308 squared. And this gives our second iteration equal to, so this is 0.5346 minus 0.056 divided by 0.4308. And this is plus 0.00265 divided by 4308 squared. And this is equal to, so this number keeps getting smaller, but it's still in the same neighborhood, 418. And this is meters cubed per kilomole. And it only wanted 2 iterations, so we're going to stop just there. So that's how to use equation of state to find our values for molar volume by using iterations and an iterative process. So that takes us to the end of this video for week 5 of ENGG 201. I hope you enjoyed, and I hope this is making more sense to you. Yeah, I'll see you in the next video where we're going to be talking about liquids, some of their basic properties, and equations we can use to define those properties. All right, that's it for today. Thanks for watching.